We're going to talk about 10.1 here. So the title of 10.1, moving into chapter 10. All right, so kind of reviewing what we've done. Chapter 8 was all about confidence intervals for one sample. All right, chapter 9 was about hypothesis tests for one sample. Chapter 10, we're going to move into both confidence intervals and hypothesis tests when we have a two-group sample, whether that be for proportions or whether that be for means. Okay, so let's read through some of this stuff. A lot of the stuff works exactly the same way. So after you feel good about chapters 8 and 9, chapter 10 shouldn't be a big stretch. Okay, so it says we compare the populations or treatments by doing inference about the difference, row 1 minus row 2, between the parameters with confidence intervals or hypothesis tests. We use the proportions of successes in the two treatment groups, p hat 1 and p hat 2, so this refers to sample statistics, this refers to the population parameters, to make the comparison. So population or treatment 1, its parameter would be row 1, and 1 can stand for whichever group you're talking about. Okay. The statistic would be p hat 1, so there's all these 1s on it because all these 1s refer to the first group. All right. Then for the second group, you'll see all these 2s on here, row 2, p hat 2, and 2. All right, so the next section of the note card just talks about the sampling distribution. What does the sampling distribution look like? All right, so the best way to think about this, the sampling distribution, is to make our normal curve as long as the data is normal. Okay, so right down the center, okay, we would expect that to be the true difference in proportions, row 1 minus row 2. And all along here, we're used to putting p hats in here, but instead of just having a p hat, that p hat actually represents p hat 1 minus p hat 2. So if we keep taking samples and looking at the differences in their sample statistics, it generates some sort of distribution. And that's what they're talking about here, the sampling distribution of a difference in two proportions. So this curve is filled with a bunch of p hat 1 minus p hat 2s. All right. So let's read the next part. It says the sampling distribution of a difference of two proportions. It says the sampling distributions of both p hat 1 and p hat 2 are random variables. Because the values of the statistics would vary in repeated independent simple random samples of size n1 and n2. How do we determine the characteristics of the sampling distribution of the sampled difference in proportions? All right. If you think back to the random variables chapter, you should recall that to find the center of the new distributions, we would just have to subtract the centers of the individual distributions. To find the new spread, or the standard deviation, we would first have to add the variances. Then we could take the square root of the new variance to find the new standard deviation. And remember, with random variables, we can never simply add standard deviations when combining random variables. Okay, so what does that mean, kind of looking down here? It doesn't matter if it's a difference or not. Okay, that's always going to be a plus. All right, so certain conditions have to be in place for this sampling distribution to be valid. Okay, we have to meet that, we're used to saying n times row and n times 1 minus row has to be greater than 10. All right, that's going to be our normal condition. But now since we have two distinct groups, all right, that both of those parts have to be greater than 10 because that has to do with group 1. And this has to be true. These two conditions have to be in place for the second group. All those involve 2s. All right. So it says the mean of the sampling distribution is just going to be the true difference in proportions. Okay. So just like we did before, on that curve, the true center would be the true difference, rho 1 minus rho 2. And we know that that thing right there is also going to be, we can also write it as the mean of all the p hat 1s minus the p hat 2s. All right. And the spread, as long as the 10% condition is met, which means that n is greater than 10n, but here we have two groups, so you have to say n1 is greater than 10 times n1, and also n2 is greater than or equal to 10 times n2. You have to meet both groups have to meet that condition. As long as that's valid, this is going to be the standard deviation of the distribution. And again, recall, all right, it's got to be a plus inside there. It has got to be a plus. All right, that's this part right here. All right, so the best way to learn this stuff is by looking at an example. All right, so here's the example. It says your friend brings 2 bags of colored goldfish crackers to your birthday party. Bag 1 has 25% red crackers and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. It says using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a separate simple random sample of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportions of red crackers. So part A. It says, what is the shape of the sampling distribution of the difference in sample proportions, and why? Okay, so if they're asking me about the shape, let's check the normal condition. All right. So what we're used to doing for the normal condition when we deal with proportions, again, is to take our n times our rho has to be greater than or equal to 10. And we also have to have n times 1 minus rho be greater than or equal to 10. But now we have two groups. So this has got to be n1 rho 1, n1 rho 1. We're going to have to do the same thing over here. And by the way, we don't know what the true rho is. So we're going to use our p hat as an estimate. All right. And the same has to be true for the other group. All right. N2, p hat 2 has to be greater than 10. And N2, 1 minus p hat 2 also has to be greater than or equal to 10. All right. So let's just let the 1 represent the bag 1. So in bag 1, I had 50 crackers. Okay, I had 50 crackers. And then the proportion that are red from bag 1, okay. Well, I guess they gave us rho. So this is not a hat anymore, I'm sorry. Okay. And they gave us rho for the second one as well. My bad. All right, so 50 times 25% has to be greater than or equal to 10. Well, a quarter of 50, half would be 25, and half of that would be 12 and a half. All right, so that meets that. And if I do 50, 1 minus 25% is 75%, and that would be 37 and a half. Okay. So I meet both of those for the first group. The second group also has to meet that condition. All right. In the second bag, there's 40 crackers. All right. And the proportion of red crackers in bag 2 is 35%. All right. 35% of 40, 30% would be 12. Add back 2, so that'd be 14. All right, and this would be 40 times 65%. All right, and that would be, what, 26? Okay, so we're okay there too. Since all those are met, we can say that the sampling distribution of p hat 1 minus p hat 2 is approximately normal. Because both groups meet the normal condition. All right, part B. So that was all part A. Part B, find the mean of the sampling distribution. So we want to find the mean of the p hat 1 minus p hat 2. Well, that's going to be exactly the same thing as the row 1 minus the row 2. Okay, that's going to be the center of that distribution. Well, what's row 1? It's right here. It's 25% minus row 2, which is right here. It's 35%. So that's going to be negative 0.10. And don't worry, you might be like, oh, it's negative. What's wrong? That's just saying in my distribution, if I take the row 1 minus the row 2, all right, we would expect the center to be at negative 0.10. Okay, that's the center. And lastly, in part C, it says find the standard deviation of the sampling distribution. So I'm looking for the sigma, okay, of the p hat 1 minus p hat 2. I'm looking for the spread or the standard deviation of this curve. I already know it's approximately normal. Okay. I'm going to use a formula for that. Okay, remember, we never, what should I say here? Okay, we have to have a plus. All right, we never subtract variances. We always add variances. Okay, so we're going to do row 1, 1 minus row 1 over n1. All right, plus row 2, 1 minus row 2 over n2. Now we do have to check a condition before we can use this. The only way this is true, the only way that's the true spread of that distribution is that if n1 is greater than, it meets the independence condition, 10 times n1. All right, and our sample size for bag 1 was 50. And 10 times 50 is 500. All right, I'm okay because each bag contains more than 1,000 crackers. So is my population greater than 500? Yes. Each bag contains more than 1,000 crackers. All right, so that one worked out. N2 has to be greater than or equal to 10 times the sample size of group 2. And again, this would just be 10 times 40, which is 400. And again, each bag contains more than 1,000 crackers. So the condition to use that's okay. Now let's actually figure it out. Okay. So to figure this out, all right, take a big square root. Okay, bag 1 had 25% red crackers. That's 25 times 1 minus 0.25, which is 0.75. Zoom in a little bit for you. Over the sample size from bag 1, which was 50, right, plus bag 2 had 35% red crackers, so 35 times 0.65, and the sample size for group 2 was 40. All right, so we can do that in one step in our calculator. All right, so it would look something like this. Put a big square root, fraction, 0.25 times 0.75 over 50, plus another fraction, 0.35 times 0.65 over 40. and enter 0.097. And that would be the spread of this because it met the independent. Remember, this is the independence condition. It's the independence condition. So now we're going to jump into confidence intervals. Okay. Now look at this confidence interval. It looks almost exactly like a one sample proportion. The only difference, instead of just having a p-hat here, you're having a difference. Okay, so that's a little bit different. And instead of just having one of these things, that's what we're used to seeing, okay, for a one proportion z interval. Okay, now we just have the other piece. And we're using p-hats here because this becomes a standard error. Because we don't know what rho really is. If we knew what rho was, we wouldn't do all this. We have the same z star. And when we do our condition check, because we don't know rho, we're going to let p hat stand in place for the different rows, for the different p hats. All right, so it's very, very similar. All right. Now, in the calculator, let's think about what this would be called. It's called a 2 prop for 2 proportion. Z, because we're going to use the Z chart. Interval, because this is a confidence interval. Same type of thing. We do our point estimate, which comes from our statistic or statistics, plus or minus the margin of error. And the margin of error is made up of those two parts, just like it was before. All right, this next thing is at the bottom of the page. Same conditions, but you got to do it twice. It's got to apply to both groups. All right, now at the top of this page, this is important. It says after calculating the interval, if the value is 0, if the value of 0 is inside the interval, that means there is insufficient evidence to show a difference. Okay, so for example, if we get an interval and it goes from negative 0.04 to, let's say, for example, 0.10, 0 is in that interval. That means the difference could be as great, the true difference might be as great as negative 4% all the way to positive 10%. All right, so if zero would be in here somewhere. So I can't tell if there's a true difference in the proportions of the two populations. And that should make sense from a theoretical standpoint. All right, guys, let's do the example. It says, and this is the same type of example, or part of the same example as we did in the previous chapter. It says, as part of the Pew Internet and American Life Project, researchers, I should say researchers, okay, conducted 2 surveys in 2012. The first survey asked a random sample of 799 U.S. teens about their use of social media and the internet. A second survey posed similar questions to a random sample of 2,253 U.S. adults. In these 2 studies, 80% of teens and 69% should say of adults, okay, use social networking sites. It says construct and interpret a 95% confidence interval for the difference between the proportion of all U.S. teens and adults who use social networking sites. Compute by hand and then verify on the calculator. All right, we're going to use that same process to go through our confidence interval, but remember, on confidence intervals, we don't have a decision to make like in a hypothesis test. Okay. All right, so our first step is to make a statement about what we're trying to do. Okay. We are interested in computing a 95% confidence interval for the true difference among teens and adults who use social networking sites. Okay, and that true difference is going to be row 1 minus row 2, where row 1 equals true proportion of teens, and row 2 is the true proportion of adults. So I'm going to let the reader know I'm defining group 1 to be my teens, and I'm letting row 2 be my adults. So that's number 1. All right. So we got our statement done. Now we got to do a condition check. Conditions. Okay. First condition is random. All right, so let's go back into the question. All right, the first survey asked a random sample of the teens. Okay, so right here I'm going to write random sample of teens stated. All right, up here it says random sample of U.S. adults. I'm just communicating with the reader that I've checked for randomness and it's stated in the problem. All right. Then we check for independence. And we have to do it for both groups. All right. So I have to make sure n1 is greater than or equal to 10 times little n1. So let's deal with that first. Remember, group 1 is the teens as I defined it. All right, I defined that the sub numbers are 1 and 2. All right. So of the teens, back in the problem, it said I had 799 teens. All right, so n1 would be greater than 7,990. All right, so now I can say population of U.S. teens greater than 7,990. I like to put a little line. Now I have to make sure n2 bigger than 10 times n2. Right. 2, the sample size for adults was 2253. So that'd be 22530. All right, and I can say that the population of U.S. adults more than 22,530. That's pretty clear. All right. And the last condition, so I got the random condition, I got the independence condition. Now I need to meet the normal condition. So I need to make sure n1 times p hat 1 is greater than 10. So if I put those numbers in here, there were 799 teens, and the proportion that used them is 0.80. All right. So I need a calculator. 880%. I'm guessing it's about 640. 799 times 0.8. 639.2. Okay. So we can say that's about 632. Definitely greater than 10. Or 639, excuse me. 639.2. All right, and then n1 times 1 minus p hat 1 has to be greater than or equal to 10. Well, if I just figured out this was 639, okay, there's 2 ways to figure this out. We could do 799.20. Okay, but these 2 numbers, 639 plus something else, has to add back to the 799. Okay, so that's just going to be 160 if I round it. Okay. So 799 times 0.8, or 0.2, excuse me, say it's going to be 160. So these both check out for group 1, but I also have to do it for group 2. All right, so n2 p hat 2 has to be greater than 10, and n2 1 minus p hat 2 has to be greater than or equal to 10. All right, so n2 was 2,253, and the proportion that used was 0.69. So this over here would be 2253. Has to be greater than 31% because that's the difference from 1. All right. So if I do 2253 times 69%, and if I round it, 1555. All right. I do the same thing. I do times 31% instead. Okay, that's going to be 698. And that's also greater than 10. So we're okay. We met all the conditions. And I know it's a pain to go through that. All right, the condition check is the worst part of this. All right, so we did our statement, we did our conditions. Now it's time for calculations. All right, calculations. All right, so this comes from two groups. So we're going to call it a 2. It's a proportion, so we're going to call it a prop. We're going to use a z critical value, so z, and it's an interval. So it's a 2 proportion z interval. Okay. And the level of confidence that we have is we want is 95%. Right. So my formula for that's going to be p hat 1 minus p hat 2 plus z star times that really big square root, p hat 1, 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. All right. So let's think about what these things are. Let's label them. All right, my p hat 1, remember that refers to the teens. All right, told us 80% of the teens. All right. P hat 2 was the adults, so that was 69%. All right, so I've covered that. Now I need to talk about n1, n2. Give these values. Okay, sample size, n1, teens, 799. In that sample, adults, 2,253. Right? So to calculate, we're also missing z star. So on my graph here, we already said the sampling distribution was approximately normal. All right. We want 95% between these values, and also 95%. So that means there's 2.5% left in each tail. So when we find this z star, it's actually going to be the left area of 95 plus 2.5, which is 97.5. Okay. So if we do that, we can do that using inverse normal. So I can go second distributions, inverse normal, area 0.975. Leave those alone, paste. All right, so 1.96. Again, you can store that with whatever letter you want, because you know you're going to need it. Store it as z. Okay, so the z star is about 1.96. All right, so now we plug and chug. We're going to do 0.80 minus 0.69. Right, sorry, plus or minus 1.96 times 0.80. 1 minus 0.80 is 0.20 over 799. All right. Plus, always plus, 0.69. 1 minus 0.69 is 0.31, all over 2,253. And this entire thing, again, remember what that's called? That's the margin of error. I usually like to find that first. All right, so our sample difference was 11%. Then we're going to give ourselves some buffer because each sample difference might be different. All right, so I'm going to take this number and I'm going to multiply it times that huge square root. So I'm going to do 0.80, 0.20 over 799 plus 0.69 times 0.31 over 2,253. Right, so 0.0337. All right. I can store that as some other letter if I want. So I can do 0.11 minus a, and I can do 0.11 plus a, and that would be the range of my interval. 0.0763 to 0.1437. So that means that the true difference could be as low as 7.6%. Okay, even though we got a sample difference of 11%, we're saying the true difference could be as little as that or as much as that. All right. So let's go ahead and write the conclusion now. Remember, in our steps, no decision with a confidence interval, straight to conclusion. Okay. We are 95% confident that the true difference, okay, in proportion between teens and adults' use of social media is between, you can say these as percents or just as decimals, 0.0763 to 0.1437, or you can say it as 7.63% to 14.37%. Okay. So there's up to a 14% difference, as little as a 7.5% difference, essentially. All right. Now let's examine our interval right here on the calculator to make sure we got the right answer. Okay, it's going to look kind of weird on the calculator how you have to input it. They didn't give me number of successes. They actually gave me a percentage here. So it's going to be a little different. You got to think on this one. So if I go stat, go over to my test, we're doing an interval. So it's not going to be anything that ends in test. Okay, you might be tempted to choose Z interval, but that's not the right one. Okay, this involves two samples using proportions. So we're going to look for 2 prop Z interval. There we go, right there, letter B. 2 proportions Z int. Okay, now they're asking for an X1, but X1 is the number of successes. You know where we can find that? Right there, 639. That's the number of successes. Okay, and N1, actually another way you can do it, just like using your calculator, because I remember I rounded that. Take 799 times 0.80. Okay, and it'll give you the exact value, 639.2. All right, the sample size was 799. Okay. Now, how many successes for adults? Well, 2,253 were sampled, and of those, 69 said so. So that's the exact number. All right, 1554.57. All right, that's why I wrote this 1555 here. And the sample size was 2253. We want to have 95% confidence and calculate. Gave me an error. I knew it gave me an error. All right, so here's how we got to fix it real quick. Stat test. It won't let me use the decimals for counts. So go back down to B. All right, just round it. Just know that your answer is going to be slightly different because in your calculations, you didn't assume rounded numbers. All right, so let's just do 639, 799, use the rounded numbers. 1555, okay, out of the 2253. All right, should work now. Okay, 0.0758. All right, notice that's a little bit different. Okay, it's a little different. 0.1432. I mean, we're not talking much difference. We're talking about like 5/10 thousandths of difference. If you rounded it to 2 places, it would be the same. Okay? If you rounded it to 2 places, it would be exactly the same. Okay. As you can see, why is it different? Because when they calculate 639 out of 799, all right, that's not quite 80%. That's only 79.97%. And when they do 1555 out of 2253, that's not quite, that's just over 69% actually, where I use 0.69. All right, so the answer varies slightly, okay, but not much. It's really not much, about 5/10 thousandths. All right. So the calculator for the most part matches. The calculator wants everything in counts, not p-hats, which is kind of, you have to know what you're doing to check it. All right, now, still in this section, they're putting the hypothesis test in there because you guys are aware of it. All right, so just like when we had a single hypothesis, and just kind of as a review, you know, maybe someone said the proportion of people who voted for a president was 60%, but you thought it was less than that. All right, that's some parameter where we think the center is in our sampling distribution. We think it is at 0.6. If we get p-hat low enough, then we can say, no, that's not true. All right. Now, let's kind of read this and think about what this is saying. Now, it says, an observed difference between 2 sample proportions can reflect an actual difference, which could be true. I mean, if you got one of your p-hat 1s minus p-hat 2s, if it's way over here, it could be the result of a real difference of the real parameter, okay? Or it may just be due to chance. There's variability. Each one of these p-hat 1s minus p-hat 2s, they're variable. They go all over this curve. All right, so that's where it says, that's why it says, or it may just be due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. Okay, so our statement of no difference or our null hypothesis is usually that the true proportions match, they're equal to each other. That's usually the situation we're in. Okay, and we have to have evidence, and if we want to rewrite this another way, guys, like if I said row 1 equals row 2, if I subtract row 2 from both sides, it gives me that statement. I'm just manipulating that equation. All right, so we're going to assume that the difference is 0, that there's really no difference between the true proportions. And our alternative is either going to be greater than, it's going to be less than, or it's going to be not equal to. That would say there is some sort of difference. One is less than the other, okay? And usually it's 0. Usually that hypothesized value is 0, all right? So just like before when we calculated a test statistic, all right, we take our statistic minus our parameter over the standard deviation of the statistic. Now, how is this different in one sample? In one sample, all right, for instance, let's say over here we got a p-hat of 0.5, for instance. Now, the way we would calculate the test statistic there is we would take our statistic minus our hypothesized parameter all over the square root of our hypothesized parameter times 1 minus it over your sample size, whatever it was. This one's a little bit different. Now our hypothesized value is usually 0. So I don't want to put 0 in here, because if I put 0 in here, the denominator is 0, and I'm not allowed to divide by 0. All right, so we got to use this thing called p hat c. All right, it's p hat c, where p hat c is the combined sample proportion. That is, p hat c equals the count of successes in both samples combined over the count of individuals in both samples. All right, and it's recommended that you follow the general SC-CDC process that you learned about before. Best way to learn this is through an example. All right. So here's the example. It says, researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend school each day, or attend each school, excuse me. Do these data give convincing evidence at the 0.05 significance level, all right, that's going to be our alpha, of a difference in the true population proportion of students not eating breakfast in the morning between these 2 schools? Okay, so let's go. And we want to know if there is a difference. All right, so let's write this. Number 1, we write our statement. In the case of a hypothesis test, those are the hypotheses. All right. So HO and HA. So what we're going to start by saying is we're going to say that the true proportion of kids who don't eat breakfast in School 1 is equal to the true proportion who don't eat breakfast in School 2. And a different way I can write that is if I subtract row 2 from both sides, okay, I would just get that. That when I subtract those 2, it would be 0. All right. The alternative hypothesis is that there is a difference, or they do not equal each other. Or that if I subtract row 2 again from both sides, it's not going to be equal to 0. All right, so this lets me know it's a two-tailed test. Two-tailed test. All right, and you should define for your reader what row 1 and row 2 are. So row 1 is the true proportion of students in School 1 who have not eaten breakfast. And row 2 is the true proportion of students in School 2 who have not eaten breakfast. It's important to define what your parameters represent. Because as soon as I tell them that row 1 represents people or a proportion in School 1, I don't have to keep referring to what N1 would mean or what N2 would mean. They're going to know that just from that alone. Okay. All right, so that's your statement. Step 2 are your conditions. And you got to test it on, you have to test your conditions for both groups. Okay, so random, all right, so random, an SRS of 80 students from school 1, SRS of 80 from school 1 stated. Okay, SRS of 80 from school 1 stated. All right. And at school 2, SRS of 150. Now, if for some reason they do not tell you that it's random, just write that you assume both samples were random. Okay, you don't want to stop the test just because they didn't put that in a question. Assume it and move on. All right, so that's the random. All right, now we have to test the independence condition, okay, which is the 10% condition. So n1 has to be greater than 10 times little n1. All right, so n1 has to be greater than 10 times 80. All right, so n1 has to be greater than 800. Okay, and it says more than 1,500 students attend each school. So 1,500 is greater than 800, so we're good there. N2 has to be greater than or equal to 10 times little n2. There was 150 sampled in school 2, so that's 1,500. And it says more than 1,500, so 1,500 would be greater than or equal to 1,500. So we're good there too. All right, because it actually says more than. Okay, so this number is actually bigger than 1,500. Don't know exactly how much, but we're okay. All right, and then we have to do the normal condition. All right, the normal condition. So we have to make sure that n1 p hat 1 is greater than or equal to 10. Make sure n1 1 minus p hat 1 is greater than or equal to 10. All right. So what is this going to be? This is going to be the number of successes. In this case, success would mean not eating breakfast, unfortunately. All right. It says 19 had not eaten breakfast. This is going to work out to be 19. Okay. And there were 80 people total in group 1. So 80 minus 19 would be 61. That's greater than 10. Right. So both of those work out. And we should check out the N2 information, sample 2. All right, so that's going to be the number of kids who did not eat breakfast from school 2. All right, they tell us that's going to be 26. 26 is going to be greater than or equal to 10, and n2 times 1 minus p hat 2 has to be greater than 10. In total, there were 150, so 150 minus that will be 124. So both of those are good too. So I've done my condition check. I'm set on that. Now we've got to do calculations. All right, calculations. This is a 2 proportion z interval, or excuse me, it's a z-test. It's a 2 proportion z-test. Right. So what this is going to mean, all right, to find our test statistic, It's good to put our alpha in here too. Our alpha was told to be 0.05. Z is going to equal the statistic. Well, the statistic would be the p hat 1 minus the p hat 2, all right, minus the assumed parameter, which in this case is this, over, we have that p hat combined thing. Okay, we have that p hat combined. So that's going to be this thing. And if you want to look, let me just look back to here real quick. All right. These are the same, p hat combined, 1 minus p hat combined. So you can also write that denominator as p hat combined, 1 minus p hat combined, times the big quantity, 1 over n1 plus 1 over n2. Okay, so I can just, since these are common to both terms, I can factor it out in front. I can factor both of those out in front. All right, that's the way I've always done it. All right, so it's going to be p hat combined, 1 minus p hat combined, times 1 over n1 plus 1 over n2. All right, so let's figure out what these things are. And then we can plug them in. So p hat 1, that's from school 1. All right, 19 out of the 80. P hat 2, that was 26 out of the 150 didn't eat breakfast. All right. What else do we need in this formula? We got p hat 1, p hat 2, n1, n2. Well, that's really easy because it's in the denominator. n1 80, n2 150. All right. We need p hat combined. So you take the combined number of successes, so 19 plus 26. All right. Over the combined total, 80 plus 150. All right. So 19 plus 26 would be 45 over 230. All right. Then you can plug it in. Okay. So Z equals, all right, 19 over 80 minus 26 over 150. I'm not going to put these in as decimals because I don't want to compound round. All over, what would p hat combined be? It would be 45 out of 230. Okay, what would 1 minus that be? Well, 1 minus this as a fraction would just be the difference in 45 and 230. Okay, so that would be, what, 185 out of 230. Okay, that would give you the same decimal. All times 1 over 80 plus 1 over 150. Okay, so that's how you're going to find your test statistic. All right, so Z equals, all right, this will be a little cumbersome to do. All right. And if you want to put them in and then get decimals, you can. So like 19 over 80, that's that. I can just store that as A. 26 over 150, awesome. Store that as B. Okay. And if I do the 45 over the 230, okay, store that as C. You'll see how I'm putting this in here. Right. So right here, I let that be A. do A minus, I let that be B, all right, minus 0 all over big square root. I let that thing right there be C, all right, times 1 minus C all over another fraction, 1 over 80 plus 1 over 150. Do that, close it off, awesome. All right, so 1.168. That is my test statistic. So I got to calculate that, then I got to show my graph. Remember, we're assuming that the center, we're assuming that the true difference is 0. So the hypothesized parameter goes there. We're at a z-score of 1.168. So if I can find this area, that's part of the p-value. However, this is a two-tailed test. So not only after you find that area, essentially you have got to double it because it's a two-tailed test. So let's find this area first. Okay, so let me store this answer as z, because that's our test statistic. Okay, now let's go to our normal CDF, and I want to go from z to infinity to get that right area with the standard normal 0 and 1. Okay, so that's this area right here, 0.12. But you got to add that area back in, so you got to double it and times it by 2. So here the p-value is 0.2427. So what does that mean? Assuming that this is true, assuming that there is no difference, there's a 24.27% chance that I would observe a difference as great as this. What was that difference? A minus B. Okay, there was a 6% difference. If there really was no difference, there would still be a 24.27% chance that I would get a difference of that much or greater on either side. Okay, that the true difference would exceed 6%. Okay, so that's the calculations, and I'll check that in the calculator soon. All right, but this is a hypothesis test, so we have 2 more parts. Part 4 is the decision. All right, here my p-value was this, is greater than the alpha. That means the p is not low. All right, so what's my decision? When the p is low, you reject. So if it's not, you fail to reject. HO. All right. And one more step, we have to make a conclusion. All right, so here, conclusion. There is insufficient evidence at the alpha equals 0.05 level to conclude that there is a difference in the proportion of students not eating breakfast between the schools. Okay, something like that. Doesn't have to be exactly like that, but say there's not enough evidence to show that there's a true difference in the percentage or proportion of students who are not eating breakfast. Okay. So that's how we go about it. It takes a lot of time. So let's test ourselves with the calculator. Let's see if we get these same things, the same test statistic and the same p-value. All right. So this is a hypothesis test. So when you go stat, and you go over to test, all right, it comes from two unique samples. So we're going to look for two. Okay, it's going to start with a 2. These involve proportions. So we're going to look for 2 prop. We are using the z-curve, so z, and it's a hypothesis test, so test. So that's the one we're going to use, number 6, 2 prop z-test. Okay, it's going to ask you for x1, that's the 19. The x2, or the n1, excuse me, that's 80. The p2, or the x2, that's 26. The n2, that's 150. All right, now they're asking about the alternative hypothesis. Row 1 does not equal row 2. It's a 2-tail, so I'm going to select that one. And you can calculate it or you can draw it. All right. I'm going to go back to that real quick. Let's just draw it. I think it looks nicer. Okay, there we go. As you can see, it's a 2-tail test. Right. It's nice when you draw it, you can make your paper match that. All right, so here it tells you Z is 1.1683. Okay, that's what we got that right. And the p-value is 0.2427. Awesome, we got that right. All right, let's keep going. So now, inference for experiments. It says most experiments on people use recruited volunteers as subjects. When subjects are not randomly selected, and a lot of times in experiments you can't do that. All right. Researchers cannot generalize the results of an experiment to some larger population. But with an experiment, researchers can draw cause and effect conclusions that apply to people like those who took part in the experiment. The same logic applies to experiments on animals or things. Okay, so you might not necessarily be able to say that it applies to all men, but you may be able to generalize some cause and effect relationship between men over 60 that have had a heart attack, for instance. That's what this is trying to tell you about. And there's more in your book about that. So it also says, also note that unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. Okay, so if there's no random selection, the independence condition doesn't matter. It's not going to play into effect. Okay, it's not going to play into effect. There still needs to be random assignment, though. You have to randomly assign people to groups. Okay. So if you think you got it, you can go ahead and stop it there. I'm not going to go over this one. It's very, very similar. Okay, we'll go over this one in class. All right, but you can try this one if you want, and if you have questions, you can ask about it. So the video is going kind of long, and I'm just going to stop it right there.